So, and I share also my screen. Okay. So we will work on RStudio because I mean I wanted to put something into practice. So we ended the last lecture with okay, let's have a little bit brief recap of what we did last time. So well, we have until now we have defined like what events are. So we have defined events. From the events, we have defined the elementary events, which depend on how much precise we want to be. So once we fix, they are defined. Once we fix the events we want to consider. Then we have introduced the sample space. We have used elementary events to define the sample space, and now we have a model that we can use to model events in the context of set theory. So we model events as subsets of the sample space. Then with the or I mean with the or is equal to the union and is equal to the intersection and so on. Then we have defined we have restricted ourselves to finite sample spaces of this form. And we have defined probabilities on omega. So we have to fix, to define a probability, we fix simply n numbers with the only restriction that pi is in 0, 1, and the sum, there is sum to 1. So p1 plus. So, and since events, for an event t, which is a subset of omega, the probability of the event t is simply equal to the sum of the probabilities of the elementary events in the set. So the sum over omega in E of the probability of omega. So, and this is what we did. And we introduced also the conditional probability. So if you observe A, so our probability changes, and the probability of A, so if you observe A, so our probability changes, and the probability of A 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 changes, and the It is usually denoted with the symbol P with a vertical bar A, and is defined in the way you would like to have. So simply that is defined in this way. So the probability of an elementary event omega is equal to the probability is proportional to actually the probability P of omega if omega is in A. So basically, if our elementary event is in A, nothing changes. But if it's not in A, then we assign probability 0 to it because we know that A happened. So this is what we did basically. And yes, we we did, but I actually didn't do it too much with too much effort. So I won't do it, but it is easy to show that this definition is the same as the following. So that the probability of a set of an event E given A is equal to the probability of E and A divided by the probability of A, which is a constant because A is fixed. E may vary. This is the definition of conditional probability. Okay, and we ended the last lecture with an example, which was a little bit creepy, and I wanted to, I rushed at the end of the example, so I wanted to do it again. Okay, now before doing that, I wanted also to give another definition. So, the conditional probability can be also, there are two ways of assigning a probability. So one is giving the probability of the events, and the other one is giving the odds. So I wanted to define what are the odds of an event, because they enter in many exercises, even if it so the computations in many cases involve the odds, even if one doesn't define them. So the odds are simply when you have to bet. So let's take E an event. So the odds of E are simply this quantity. Um, is the ratio between the E and the measure of E and its complementary. So why this definition? Well, actually you encounter this number in many cases much more frequently than the probabilities of the events. Why? I mean, you don't have to do it, of course, but if you ever betted in a match, for a football match or whatever, usually a bet goes in the following way. Well, you gain an amount of money which is X if E happens. So, okay, no, for each ruble, for each you gain X if E happens, and you lose the ruble uh, if E doesn't happen. Um, so this is usually how a bet goes. So E can be like, I don't know, Real Madrid wins the Champions League. So um, how uh, how is a bet? So a bet has to be fair. So actually, it is not because the, I mean, the one who assigns the bets we always wins. But in principle, it has to be fair, meaning that the expected value, the expected return has to be zero. What is the expected return? Well, it is this quantity. Uh, well, it is what you expect actually. So it is what you win times the probability of winning. You win only if E happens. So the probability of winning is the probability of E. Plus minus what you lose, the probability minus what you lose times the probability of losing. So you lose 1 ruble, and the probability of losing is the probability that it doesn't happen. This is the expected return. And you want it to be zero. Why? Because if it is greater than zero, then with the bet you expect to win. If it is lower than zero, then you bet the other way around. So, I mean, usually you can bet in whatever for whatever event you want. So if this x is positive, if this expected return is negative, then you do the other bet. So it has to be zero. And the only way, well, you solve this equation. So uh, equal to zero, and you obtain that x has to be equal uh, to the complementary of E divided by of E. So if X is the reward for winning uh, the bet, then like okay, maybe so Okay, x is equal, yes, it is correct. So, like, if you win x, if you point 1 ruble, okay, so probably, am I wrong? Okay, probably I'm wrong in some sense because, well, this is the expected return. Okay, the number you see in the bets is not this number x. It is x plus 1. Okay, so yes, you always, I mean, the one ruble you put here should be also so you win. Okay, yeah. No, it is. So can it be less or equal than 0? X? No, I mean, oof. So I wanted to connect it with the number you see in bets, but probably I'm missing something because now this x can be between 0 and 1, and usually you always see a number greater than 1. So this is usually the number you see in bets is x plus 1. Uh, these are the odds. The odds are x. The odds of E are x, and the number you see on bets is x plus 1. So why I'm telling you this? Well, I mean, they have a very uh, like it is they have a really easy interpretation, which is this one. So it is the fraction of the area. You can think of the probability as an area of the complementary phi divided by the probability of phi. So it is a ratio between two areas. So assigning, what I wanted to say is that assigning a probability is the same as assigning the odds of each event. Um, this is simply because you can rewrite in this way the probability of phi is equal to the probability of E divided by the probability of omega, which is 1, because the probability of omega is 1. So this is equal to the probability of E divided by the probability of E plus the probability of the complementary. And now you can take as a common factor the probability of E So you have this chain of equalities. Now, on the right-hand side, you have the odds of E, and on the left-hand side, you have the probability. So assigning the odds is the same as assigning the probabilities. There is no conceptual difference, but they are the same thing, but with two different perspectives. So these are the odds. And why I wanted to tell you this? Well, because in the example we did last time, we were, I mean, we in this kind of exercise, sometimes it's better to reasoning with the odds, and because also there is, when doing the conditional probability, you have a really nice interpretation. It is easier to interpret conditional probability in terms of the odds. So let's see why. Let's compute the odds of the conditioned event. So do you have any question until now? So with the definition of odds, the everything is fine. So if it is, so it's simply a definition. So nothing, if it is fine, I go on. If not, this is the time, the right time to ask. So, okay. Are you, I mean, if really, if there is any question, just ask, because otherwise I go on and then at some point it will become difficult, and then it's difficult to come back. But if not, I can repeat whatever, just okay, so we have the odds, and let's see how odds change if we know A. So let's compute the odds of E. So the definition of odds is this one, the fraction between E, the probability of E given A, sorry, the probability of E, the complementary of E given A divided by the probability of E given A. Well, but this is equal to the probability of the complementary of E intersected A divided by the probability of A times in the denominator we have the probability of E and A, while in the numerator we have the probability of A. Now we simplify the probability of A and we get that is this ratio. So we see that what do we do when we do a conditional probability? Simply take the same odds, but we forget about what's outside A. So basically, the odds are the odds obtained if we forget about A. So to have I mean, I made a very bad picture. So we have, I can copy and paste it. So, well, uh, if these were the odds of before, so the probability of the complementary phi divided by the probability of phi, well, if A happens, now we forget about everything that's outside and we compute the odds of this small of what's left. So you see that odds can change very much if A, for instance, if A is contained in E, the odds will be zero. So they can change, they can vary, this number can vary from 0 to plus infinity. So if A is chosen appropriately, you can obtain whatever number between 0 and plus infinity. And this is simply, so this is really, I mean, it's a matter of, so with a picture, you can easily see that simply a proportion of areas. So nothing deep, but I mean, but it's useful because now we can come back to the example of to the end of the example we did in last time. So, which was a judicial case, which was a tricky example because there was an event A, so probably, see, let's call it A, which is a woman has been killed. Then the principal suspect is the husband. So they do some investigations and they discover the following fact that the husband used to beat his wife. Now, every so the what's the defense argument? So the defense argument was that they report some statistics that tell that so only 1/10,000 men that beat their wives end up killing them. So this was the defense argument. So how can we restate this defense argument? Well, let's say that is the event that the husband killed his wife. So the defense argument is that the probability of P given B is equal to 1/10,000, which is not enough to say that somebody is guilty of, I mean, is guilty of course, of beating his wife, but not of killing her. So in practice, we are like in this situation. So like okay, like in this situation, the probability, okay, maybe in this one. Mm, okay, so probably I missed. Okay, we were here. So now, well, what's happening is that we are forgetting the most important information we have. We have that we know that A happened. So basically, we have to compute actually this one, this probability. And now you will see that, as in this example, that the odds change very much. Now, if we add also A, the odds will drastically change. Why? Let's do the same computations as before. This is equal to the fact that this is equal to, by definition of conditional probability. So, do you agree with this? Yes, this is the definition. And well, now A is a subset. A is the fact that the woman has been killed. So it contains B, the fact that the husband has been killed. Cioè that the husband killed her. So we can simply rewrite this as um, and copy and paste it. By and removing okay, sorry, no, B is not. Okay, did you spot the error? I could say I did it on purpose, but it is not true. So I mean, B is another event. Is E dot. It's a subset of. Uh, can you see my screen? Is it? Mm, okay, no, it was. So it stopped sharing for a moment. So, I mean, are you, is anybody there? Just,
Yes, we are.
okay, perfect. Thank you. Okay. Uh, now, now here. Um, okay. Um, okay, sorry. Now, we can simply remove A intersected E is simply A. So we can remove this one. And now we can, sorry, it's C. And now we can go on and simply write A as A minus E plus and sorry, or E. So if we use this, we get that the probability continuing with this chain of equalities we obtain that on the numerator E and B. And on the numerator we obtain using the additivity, that is E and B plus what's left of A, which is A minus B, A minus E, and B. So this is equal by additivity to this. Let me put the parentheses in a better way. So now, well, we can take as a common factor E given B, and we will see that the odds will appear naturally. So we basically are doing the same computation as before for the odds. This is equal to, so 1 divided by 1 plus the odds of E. So A, the complementary of E in so we obtain this equality. Well, now we can simply yes, what we can do here, well, we have an estimate. The defense kindly gave us that the statistics, so that E given B is this number here. Well, so we go to the pass to the conditional probabilities, and we say that this is equal to the fraction of 1 divided by 1 plus we simply multiply and divide by b to get the well, do you remember that the odds of an event given b are like of the condition? I mean, it's simply multiplying and dividing by b in this fraction that we obtain on the numerator e a minus e given b, and on the denominator e given b. Well, now how can we estimate the term below? Well, we need to estimate only, we know an estimate for the probability of E given B, because the defense provided us with it. We need to estimate the following quantity. The probability of A given given B. So how can we do this? Mm, mm, so we can simply say that okay, this is equal to so we need simply to we need to bound it from above. So it's we need to take so we need to say that this is less or equal than a quantity, a small quantity. Well, this is okay. Let me see. Let me check. I have it written here. So why you can otherwise I will do a mess. So I didn't write. Okay, sorry. So how can we estimate this quantity? Well, where was it? Here, sorry. Well, this is equal to the probability of E that somebody else killed her, given that his wife beated her. So this is for sure probably um, we can estimate, I would say, it with simply in this way. So we say that this is smaller or equal than the probability that a woman has been killed, given that her husband kills her. Ah, okay. Her husband kills her, and this is beats her, sorry, given that, and this is equal to, we can say that, okay, no, we cannot say that the events are independent. So probably we want to say that, okay, no, sorry, let's go back, okay. Oof. Maybe I will look at it at the in the in the interval, because I'm kind of messing up the things. But so I will finish it later. Otherwise I will do a mess. So we need an estimate from above of this step here. So let's go on and let's do some programming actually. So so the computer is sampling from the computer. So from performing experiments on the computer. So we have a computer is able to perform an experiment whose sample space is discrete. So in this case, we will write the usual stuff that omega is equal to the set of outcomes and how does it do this experiment? Well, it's simply so let's define first omega. So let's take n to be equal to 10, and omega is equal to simply 1 to n. So let's see what happens if we do like this. Well, we can plot omega. Okay, so omega, okay, instead of calling them omega 1, omega n, we'll call them 1 to n, but they are elementary events. Now, of course, it's able to perform an experiment whose sample space is discrete and whose probability for which the probabilities are p1 n. So let's define a vector of probabilities. Okay, so let's call them p. And this is a vector of 10 elements because we have 10 elementary events. So let's define them in some way. So what's wrong with this p? That so so do you have? I mean, why is it not? What property does it? Uh, does it not satisfy? So oh, so I'm giving a vector. This p are the probabilities of these elementary events. But of course, they are not even less than 1. So how can we transform p to a probability? So do you have any ideas? So I give you 10 numbers which are positive, and they don't, I mean, they're not a probability. Why they are not a probability, and what can I do to solve the problem in the without changing? Of course, I could put whatever probability change, but I want to keep these numbers. So what's the best thing you can do? So the numbers are this one in P. So I assign to 1 the probability 10, so it's not possible, to 2 the probability 20. So what should I do? So do you have any ideas? So this number p represent the probability of the elementary events. Do you, I mean, and I want to build a this computer will be the computer will be able to generate an elementary event between these 10. So 1, 2, 3. It will select one of these numbers with the probability that I give to them, that I feed to it. But if I feed this probability to the computer, why he won't accept it? So why? Let's try it. I have to sample from omega with vector of probabilities given by p, and I sample only one element. So what this command will tell me? So let's see what sample does. I mean, is anybody there?
Maybe the problem is that the probability should be less than 1, and we need to divide each number by 100.
Yes, exactly. Not less than 1, but exactly 1. So let's see this sample. So I mean, it's precisely that. So these probes. So this sample takes a sample of the specified size, which is 1, from the elements of X using, let's see what is prob. It's a vector of probability weights for obtaining the elements of the vector being sampled. A vector of probabilities has to be, so the probabilities have to sum 1. And we need to divide, of course, as you said. Now, why is not working this? Maybe I need to open the file again. No, yes, so I need to change p and divided it by its length. So not length, it's sum. So now it's a vector of probabilities. Sorry, not here. The notation is the following, so let me come back here to the error. So so now I assign these probabilities, and now they sum 1. sorry, probs is without the S. Now this is the vector of probabilities and the sum of it is 1. And it maintains the proportion since we are dividing each weight by the same number, which is the total mass, this sum P. So, and the computer will give us an element which is random. So it performs an experiment, a probability, and it gives you this elementary event, 8. So we have, we have something that reproduces our model that we explained in the last lectures. So this is nice, and we can check many things. For instance, let's do an exercise. I don't know if you have if you have RStudio there to compute, to do some computations. So, for instance, if I put here 200, 1000, what do you think will be the number which will be most likely happen? It will be most likely happen this, the position here is the 6th position, so it will be 6 probably. Yes, and if we do many times, it will be many times 6, and then because it's very, and then of course, okay. So it's much more probable 6, but 4 it's also a possibility. So now, I don't know if you have RStudio, otherwise it will be difficult to do this exercise because, let's assume we observe, say, this event. So we know that A happened. Now, define the sample from the conditional probability. So define the conditional probabilities, and sample from them. So this is the exercise. There are many ways to sample from the conditional probabilities, and the idea is to now to see 2 of them. So maybe, I don't know, let's okay, so do you understand this piece of code? It's important. Do you understand what is doing? So if not, I repeat it. I can repeat many times stuff, but if it is clear, I go on.
No, please, can you repeat it
Okay,
for the last time?
Yes. No, so this. So here I'm simply defining n, and here I'm defining the vector, this vector omega, which is the following. Now, here I'm defining a vector of weights, so which is the following one, p. So let's check that the sum of p is 1. because I've divided it by its sum, so its total sum. So the sum of these entries is 1. It is a perfectly legit probability. So now we have some numbers to 1 and 1 to 10, and we attach to each of these numbers a probability. What sample does is that the probability is the following. It gives you one number. Why 1? Because we placed here a 1. So with the following properties. So it is between 1 and 10. Why? Well, because omega is between 1 and 10, and we put it here omega. So it gives you a number that is in omega, simply. So sample takes one number in omega, and we gave to them p. So what does this p do? Is simply that sample this number is equal to e. So it's this number is equal to omega e. So what is omega e? No, I made a bad choice actually. Omega e is equal to e. So this number is equal to omega e with probability p of e. So for instance, it is equal to 6. So let's write it here. Omega 4, it is equal to omega 3 with probability p of 3. So with very small probability. And let's check that 6 has a very high probability. Omega 6 is equal to the probability that this number is 6 is equal to p6, which is 0.83. So pretty much likely. So do you understand? I need to pass to this sample a vector of a vector, and this sample gives me an element of the vector with these probabilities here, p. So it's simply, I mean, is it clear, more clear now?
Yeah, thank you.
Okay, perfect. So what do you think it happens if I don't put here a p, a prob? If I don't put anything here, I put a replace. I mean, it will be the uniform probability. So each element of E will be equally likely. So, okay, it will be the uniform probability, but let's put it back our vector P. Now, how can we define this conditional probability? Well, let's actually, the definition is really, it's much more understandable in this way, because we simply need to define Q. How do we define Q? Well, we take, let's first define Q to be 0, just to allocate it. A vector of zeros now. So simply to allocate it with zeros. So, and what do we do? Well, we say that Q, well, from 1 to 5, we simply put the elements of P. So now Q, it's only a vector of zeros. Now we put this assignment here, and we see how Q changes, and it obtains the values of P in the first 5 components, and the other ones are 0. Well, this is what we want, because we want to define the conditional probability, but there is the problem that they do not sum 1, so we have to normalize it. Now, the sum of this Q will be equal to 1. So this is a perfectly legit probability, which assigns 0 to the elements outside A. And this is the conditional probability given A. And we can sample from it. So we can take a sample one, and now instead of P, I put Q. So now I'm sampling from the conditional probability. So you see, I will never obtain an element greater than 5. So does it make sense? Do I need to repeat it? Makes sense. If it makes sense, I go on. I don't, okay, maybe let's, okay, I will give you an exercise and then let's make a break. So I will check also the previous example, because I forgot how to estimate the last event. So the exercise, actually I will put it on the chat. So how can I do it? Stop sharing. Yes, probably this way. Okay. So need to so so the exercises are this one. So I also share the ones for next week. No, maybe I need to change the one for next week. So let me simply go back to, so the exercise now, it's actually nice, because at the first time you see it, it's a little bit, if you didn't see it already, it's a little bit surprising, let's say. So is the following. So there is a family with 2 children. With 2 children, tells you that they have a male child. What is the probability that also the other one is male? So this is kind of, I mean, so let's, I mean, you can do the computations. You can do the computations actually. But I don't know. Maybe I will give you. Okay, and the other question is the following. They tell you that their first child is a male. What is the probability that also the other one is male? So you have to pay attention in how the information is given to you. So actually, so the second sentence contains more information than the first one. So I mean, and this actually reflects to with. So let's. I will give you time, but let's like simulate in some data about 2 families. So let's say that you go to the register of Moscow. I don't know how many inhabitants Moscow has, so 12 millions, I guess, officially. Then unofficially, maybe even more. So let's take the vector of genders, which is let's say it's male and female. And let's generate artificially okay, these are the number of inhabitants of Moscow, but maybe the families with 2 children are much less. So let's say that families with 2 children are let's say 1 million, which is I guess too much. But we generate artificially a data set that tells you whose variables are the gender of the children of a 2 children family. The rows usually denote different families. So let's take a sample from the vector of genders of size n. Replace equal to false because we need, let's save it to first child, gender first child. And let's do the same for the second child. then we bind together these two columns. So let's say table so and let's save it into two children family. So table. So let's plot it also to see what they do. So the place has to be equal to true. Sorry. And I cannot give a number for a name. So I generated a fake dataset, an artificially generated dataset of families with two children. So we will use it later to solve computationally this exercise. But you can do the computations actually. The result is here, one third, and here 1/2. So like the probability of the fact is that in the first case, they are not telling you which one is a male. So you have, you still, I mean, it's much more probable to have that the other one is female because it could be, I mean, it's simply a computation. They can happen 4 cases, so male, 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 female, female, male, female, female, and you know that these 3 happened. They they tell you an event which has probability 3/4. So and so you know it happened that an M FM happened. Instead, here you know that MM or MF happened. So that's the difference. Does it make sense? If I need to repeat something, I can repeat it. So, and how can you see? How can you see this, that this is true? Well, you simply go here. And what do you do? Well, from this huge data set, you filter the families with one children, for which one children is male. So let's take these 2 children families. And let's choose one for which either first child is equal to male, or which is written, I guess, with a vertical bar, I guess, of the one for which the second child is a male. Let's check if it is correct. Okay, maybe, or it's written in this way in here. I don't remember it. Yes. Ah, no, a table of 1000 rows. Sorry. Mm, I don't remember how or is written in MATLAB, in sorry, in RStudio. So or aliases. I have to use Magritte, the Magritte package. So I guess Magritte or let's see. No, your no, sorry. I'm doing a stupid mistake. This notation is correct. This tells you, this gives you a vector of, okay, I need to do, I guess this, I need to use this notation here. No, I need to, and so the columns will be, there are two columns, so I need to use this notation here. I expect, okay. Yes, there are two columns, so I need to put the indexes, two indexes, and here I put, I take only the columns. Okay, let's check what this operand does. It gives me simply a series of true or false, where if this condition is true, it gives me back a true. Here, if the condition is false, it's true. So this will give me a vector of true or false and falses. And I will keep only the rows which have a true. So I will keep only the rows with one male. So here there are a lot of, there are this number of rows. Well, let's check that this result makes sense. So what is the, from these are what, 750,000 rows, more or less. Let's filter further. So let's this is these are families with one male. And let's take the families with two males. better simply. Let's take, we have to have in the condition, instead of first child equal to male, or second child equal to male, or second child equal to male, we need to have an and here. So an and is written in this way, I guess. And let's check if it is correct. It seems yes. It is. So let's check how the number of elements of each one of these vectors. So the number of elements, I guess, is computed using length. Let's check if it is correct, this notation. So not length, but I guess number of rows. And row, yes. Um, so not to children, sorry, not to children families, but I want to compute how many families have two males. So two male children. So families with two males. So these two numbers are, so these are the numbers of families with two males, and these one are the total number of families with only with at least one male. So what do you think we will get if we divide these two numbers approximately? Do you have any idea? So does it? What do you think? Do you, so are you still there?
Yes, we're still here, but I personally don't have any idea.
Okay, perfect. I mean, not perfect, but it gives me the chance for repeating. So let's so do you this data set did you understand the data set like this data set here? Maybe I can put it in a better. I generated random data with I mean in the same way which should mimic like the real data about two families with two children. So visualize maybe head children families. So it is a data set which contains the genders of their children. Now I want simply to see that sampling that the condition that that there is one male child doesn't I mean leaves you like one okay, let me say it in terms. I want to sample from the conditional distribution. So I want to sample, I want to take only the families that have one male children. one male child or more. Sorry. So let me write it. It's better. So I want to check the fact the results of the exercise. That is this one, that male, if they tell you that they have one male one male child or more, or two, at least one. One male child, the other one is a male with probability 1/3. So you can do the computations because this event has 3 elements between the sample space. So the sample space is the one MM, MF, FM, FF. Each element has probability 1/4 because actually it's a little bit more probable to have a female children, but a little so. But each element is let's say that it's 1/4. So this is the vector of probabilities, and I've generated this data set by assigning to each row a probability of 1/4. So here we see no different, like the number of times we will see FF will be approximately 1/4 times we will see 2 females, 1/4. So let's check it. So I've generated a dataset using these probabilities. And now, so let's check it actually. So let's take let's, for instance, see how many, so how many say families with 2 females we have. So we have to filter, we have to replace the conditions and run this code, and we see that so let's count the number of rows, the number of families. This counts the number of families with 2 females, and the rows, and I have to put let's see what I did wrong. And row maybe. Yes, there are approximately. So this is 1/4 of the total. So let's divide it by the number of rows of the dataset. So of families, two children families. So approximately is 1/4. This is 0.25. This means that what you expect that if they tell you just I have 2 children, you will assume that the probability of seeing 2 females is 1/4. This is what you expect. But if they tell you now one more information, they tell you that they have 1 male. So now they tell you, so this is what to expect. Uh, 1/4 of the total families of the families with 2 children have 2 females. Now they tell you that they have at least 1 male. Well, now how you have to change your dataset. To change your dataset, you simply remove the data that does not satisfy this condition. And is what we did here. It's what we did defining this condition. Is what we did defining this one. You see, the condition is that either the first child is a male or the second one is a male. Okay, now what does it mean, the conditional probability given this event? Well, it means that we do the same thing we did with the original data frame, with the original data set, which was the number of families with 2 children, but with this new data set, which is the number of families with at least with 2 children, one of which is male. So let's simply depict for a moment this two children, not two children, families with 1 male. So we have removed, for instance, the first column, the first row. And now we do the same thing. We sample, we want to see how many, for instance, how many families with 2 males are there. We simply, we've seen it. So let's take this one, families with 2 males. So maybe it's better to do in this way. Let's define the families with 2 the new data frame. So new data set. The new data set is the families with 1 male. And then from this one, we want to see how many of them have 2 males. So let's take this new data set. Okay. Mm. Okay, probably. Oof. Well, at the end of the day, let's see, let's avoid this. I don't understand though why it's different from before. It's exactly the same. So from this data set, no, it's not exactly the same because first should give me the same error now, of course. But before there was here families family with two children families. And so, and coming back to what I wanted to show is that sorry, the number of families with two males is 1/3 of the total number of families with two children, with at least one male. So the number of families with two males is the number of rows of the data frame families with one male with I don't remember what I said, but this is the number of the number of families with two males, and the number of families with at least one male is this one. With at least one. So now, is it not clear what should be here? More or less 1/3, which is more or less because these are 1/4 of the total, these are 3/4 of the total. So 1 divided by 4 divided by 3 divided by 4 is equal to 1 divided by 3, simply for that. So maybe let's take a break. And okay, it may seem that this has anything to do with linguistics, but it actually, I mean, actually has. I mean, whenever you have data, this is like a kind of data. I mean, now it is not linguistical, but it's about children. But okay, I mean, it will make sense when you do some data analysis on linguistic data. So see you in 15 minutes. Okay. And if you have questions, please ask me. Just ask.